Students, good morning.
Good morning, sir.
Good
Okay.
morning, sir.
Yeah, good morning, ma. So, in the last class, we have decided and sorry, we have discussed about the temperature distribution, okay, in a plane wall, and we have discussed about the expression for the heat conducted through a plane wall from one side to another side. And similarly, we also discussed about the overall heat transfer coefficient, right? Suppose if we have one hot fluid on one side and one cold fluid on another side, we know that usually heat transfer from the hot fluid to the cold fluid, and the hot fluid temperature will be different, and the inner wall temperature will be different, outer wall temperature will be different, and the surrounding atmospheric fluid or atmospheric air temperature will be different. Am I correct? Am I correct, students?
Yes, sir.
Yes, sir.
In that case, we will be having three resistance, one offered by the hot fluid, which depends purely upon its convective heat transfer coefficient value. The other one, the thermal conductivity of the material. Okay, so as I mentioned earlier, if the material is copper or silver like that, then the heat conducted to the outside will be much more higher. Suppose if you have an insulating material, then that is the heat transferred will be lesser. Okay, and similarly, the outer fluid, if we have a fluid with a higher heat transfer coefficient, convective heat transfer coefficient, then the heat transfer will be much more higher. Okay, so this is what you have to understand. Okay, in this type you will be having a combination of conductive resistance as well as convective resistance. What are all the which one are convective resistance, my here? Can you tell me which one is convective and which one is conductive here? Anyone?
So
What here?
center one is conductive, sir. Rest are conductive.
Which one is conductive? Central one is conductive. Remaining other
Rest
two,
are
the inner fluid and
conductive.
outer fluid, is convective. So I already told you that whenever we have a solid and a fluid, usually the heat transfer is by means of convection only. Okay, and when we have two or three sets of solids which were binded together, then we will be having heat transfer by means of conduction, and it depends upon the thermal conductivity. So L by Ka is nothing but the conductive resistance, and 1 by Ha is nothing but the convective resistance. All of you are able to understand this, students? Last class we did we did one problem. Am I correct, students?
Yes, sir.
Am I audible or not here?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, ma. So finally, the heat flux or the heat conducted. Okay, heat conducted is calculated by uh, T infinity 1 minus T infinity 2 divided by sigma r. Okay, where sigma r is nothing but sum of total resistance, and T infinity 1 and T infinity 2 is nothing but the temperature difference between the inner fluid and the outer fluid. Or in other words, the heat conducted is equal to T infinity 1 minus T1 divided by 1 by Ha, by considering the first fluid alone, and by considering the wall alone, it is T1 minus T2 divided by L by Ka, the conductive resistance. And when we consider the fluid alone, outer fluid and wall, then we will be having T2 minus T infinity 2 divided by 1 by H2A. Okay, so when you add all these things, we will be getting Q, finally Q is, which is equal to T1 infinity 1 minus T infinity 2 divided by sigma R. Okay, where sigma R is nothing but sum of the total resistances. Suppose, and we also discuss about the overall heat transfer coefficient, and this overall heat transfer coefficient is a terminology which is often used in heat exchangers. Okay, so Q equal to UA del T here, whereas in case of heat exchangers, Q equal to UA del T LM. Okay, so the U gives us an idea about the overall heat transfer coefficient, which involves both conduction as well as convection resistances. Okay, and we know that U, which is equal to 1 by sigma RT into total, RT is nothing but the total resistance into A, or Q equal to 1 by R total into A. Okay, so R total is nothing but 1 by H1, 1 divided by 1 by H1 plus L by K plus 1 by H2. Okay, so that is overall heat transfer coefficient, and UA is, has the units watt per Kelvin, and if you take the U alone, then it will be having the unit watt per meter squared Kelvin. Okay, so the overall heat transfer coefficient will be having the unit same as that of the convective heat transfer coefficient. So the convective heat transfer coefficient, we have the units as watt per meter squared Kelvin. Am I correct? You can see here watt per meter squared Kelvin. Okay, the same unit is applicable for overall heat transfer coefficient also. Okay, so thermal conductivity unit is watt per meter Kelvin. Ma, students, am I correct?
Yes, sir.
Yes, sir.
Okay, thermal conductivity is K will be given in watt per meter Kelvin, whereas H will be in watt per meter squared Kelvin, and similarly U, overall heat transfer coefficient, will be in watt per meter squared Kelvin, or UA is will be in watt per Kelvin. That particular thing you have to understand. Units are very, very important. And when we take a composite wall, even in the earlier classes I have told you, suppose if you have a refrigerator, right? And the refrigerator wall is assumed to be especially the door of a refrigerator is assumed to be a composite wall. Even when you look into the Sachdeva textbook, they used to give one problem like this. Okay, the wall of a refrigerator is made up of three layers. Okay, one, the outer, the other one will be a layer where you will be having the air gap, and the third one will be a inner one which is made of a insulator. Okay, so like that it will be, the problem will be, so usually you will be, in some cases, in practical cases, you will be having inside between two layers you will be having vacuum, or you will be having air gap. Okay, so the purpose of using the air gap is to reduce the, we know that air will be having very lesser conductivity heat transfer coefficient. Okay, so what happens here is, so that will lead to lesser heat transfer inside from outside. Okay, the purpose of refrigerator is to keep the object at a cold state inside. Okay, so the temperature of the object which we place should be lesser than the temperature of the surrounding. Okay, so if we design, if we try to design the wall of a refrigerator, then it should be a composite wall. Similarly, the brick, the house in which we live in. Okay, so it is made of bricks, it is made of sand, it is made of cement, mortar, okay, cement concrete mix. Okay, or everything is there, right? So again, the wall which we live in, right, especially the wall which we construct in our houses, okay, again it's also termed as a composite wall. So that, and usually often in villages we used to see some of them, they used to have this mortar, instead of cement mortar they will be using calcium, right? The purpose of calcium is it actually the thing is it acts as a very good binding material, that is a civil property, and similarly it also often makes it cooler, right? It's the purpose is, usually calcium will be white in color, so that what happens is the white reflects the sunlight which falls on the building, so that it makes the building cooler also. So heat transfer property is also there, right? So that is also very, very important. That particular thing you have to understand. Okay, so in the day-to-day life applications, we have so much so many things where we apply the concept of heat transfer. Okay, suppose if you have a composite wall, as I mentioned earlier about refrigerator walls, as well as the wall of a building. Okay, so it is made of composite layers. Okay, so what even the nuclear reactor vessel and nuclear shielding, I don't know how many of you have studied, did you study power plant engineering, ma, all of you?
No, sir.
Did you study power plant engineering?
Yes, sir.
Okay, have you studied, discussed about nuclear shield? What is the purpose of nuclear shield? What year? You study something and forget all those things in the previous semester itself. Am I correct? When you studied this power plant engineering? In the fourth semester or fifth semester? Hello?
Listen,
Huh?
Fourth, sir. Fourth.
Fourth semester. So now in the sixth semester, you forget all those things, right? So again, the nuclear shield is again, it can be taken as an example for composite wall. So what happens is, usually the composite wall is the one which will be having, which will be constructed of three different materials having three different thermal conductivity. So the first material will be having thermal conductivity Ka, second material will be having thermal conductivity Kb, and the third material will be having thermal conductivity K suffix C. Okay, even the steam pipes with insulator surrounding it can be taken as a that is if we take the construction alone, it can be taken as a composite wall, but we will be discussing it on composite cylinders. Okay, we will be discussing about tubes, and we will be discussing about insulators over the tubes. Okay, and we will be discussing that in composite cylinders. So when we take about composite wall, as I mentioned earlier, the wall of the construction wall of a buildings, okay, commercial buildings, can be taken as composite wall. Okay, and each and every layer will be having different thermal conductivities. Okay, and you will be having hot fluid on the inner side and cold fluid on the outer side. Suppose if it is a commercial building, then you will be having cold fluid inside, because we will be having air conditioning systems inside. Am I correct? Conditioned air inside. See, now Rose, whether we have it or not. ACs, air conditioners.
Yes, sir.
All of you are there or not?
Yes.
Yes, sir, we are here.
Immediately I will be asking you some questions, ma. Please understand. I will call you your names and I will ask you some questions. Please understand. So when we talk about the commercial buildings, what happens is usually we will be having air conditioners in our buildings, so that the conditioned air will be circulated, and the conditioned air will be at 23 degrees or 24 degrees. Similarly, now outside during summer, what happens is the temperature will be 40. So the composite wall restricts the flow of the there is a flow of heat from outside to inside. Okay, so uh, that is the purpose. And how much heat is penetrating inside or transferred inside depends upon the thermal conductivity of the wall which we have constructed. Okay, so when we take a composite wall like this, and if you have water fluid on one side and cold fluid on another side, so naturally heat transfer takes place from hot fluid to the cold fluid. Okay, so now what happens here is, again, the heat conducted qx in the x-axis direction. Again, I'm saying in one direction, one particular direction. Okay, so we are considering only one dimension. We are not considering three-dimensional thing. And I have already told you in the previous classes, we have got this. We have from this equation, the basic equation is this one. Okay, we are neglecting the y-axis, we are neglecting the z-axis, and we are neglecting the internal generation, and we are assuming steady state. Okay, we are assuming steady state. When you assume steady state, what will happen? When we assume steady state, what will happen?
Sir, the
Hello?
right hand side equation is
The
zero.
right hand side, dou T by dou T, variation of temperature with respect to time. Capital T stands for temperature, small t stands for time. Okay, the variation of temperature with respect to time becomes zero. Internal heat generation becomes zero. These two things gets neglected. The equation becomes dou square T by dou x squared equal to zero. From that only, when we double integrate it, we will be getting this solution. Okay, so you have to understand, from that only we are getting the resistance, and for a simple wall the resistance is this, but for a composite wall like this, we will be having resistances like this. Okay, so now we know that the total heat conducted will be T infinity 1 minus T infinity 2 divided by the total resistance. The total resistance is nothing but uh, total resistance sigma RT is equal to 1 by HA plus 1 LA by KA plus LB by KB into A plus LC by KC into A plus 1 by H2 into A. Okay, so this is something about the composite wall. Suppose if the composite wall is like this, you can see here. Okay, if the composite wall is like this, you will suppose if it has instead of three materials like this, if it has got four materials, and the first top 50 percentage, if it is constructed of material with thermal conductivity kb, and the bottom 50 percentage, if it is constructed with material k suffix c, then what happens here is, we know that then the circuit will become like this. Am I correct? Series parallel
Yes, sir.
circuit. Okay, in electrical, you might have discussed this, the series parallel composite wall. Okay, so the series parallel composite wall will be like this. So you will be having one resistance, you will be having the outer resistance, and in between, say the inner wall resistance is this one, LA by KA into A suffix A. Okay, and LD by KD into A suffix D. Okay, and then we will be having a parallel circuit here. Okay, so to find out the resistance of the parallel circuit, we know that how to calculate. So the parallel circuit will be the resistance of the parallel circuit will be calculated like this. So the total resistance, hello, am I audible?
Yes, sir.
Yeah. So now what happens here is, if we have the circuit like this, kindly bear with me, my system is so slow.
It's fine, sir.
So if you have the resistances like this, okay, so now you can have this RA and this is R suffix D, and this is RB and this is RD. Now we know that the total sigma R, which is equal to RA plus R suffix BD plus R suffix D. Is it visible, students?
Yes, sir.
Is it visible?
Yes, sir.
And we know that, especially for this particular circuit, we know that 1 by RBD, which is equal to 1 by RB plus 1 by RD. Okay, after getting this, okay, so after getting this 1 by RBD, then you have to get RBD, or in other words, R1 by RBD will be equal to RB plus RD divided by RB RD. Am I correct? Am I correct?
Yes.
So which implies RBD will be equal to RB RD divided by RB plus RD. Okay, so like this you can find out RBD, and we can know already what is RA. RA will be equal to LA divided by KA into AA. Okay, and similarly R suffix D also we know that, sorry, this is C. I have taken C. Assume this is C. I'm sorry, I have put a D here. RA, RB, RC, and then RD. Okay, and RBC, which is equal to, I think now it is correct. Am I correct?
Yes, sir.
Please correct me if I am wrong. Okay, so similarly R suffix D will be equal to LD divided by KD into A suffix D. Okay, and RA resistance is equal to LA divided by KA into A suffix A. Am I correct? Am I correct, students? You
Yes.
can take it as
Yes.
the first resistance is RA, second one is a parallel one, which is a combo of RB and RC, and the last one is RD. So the summation of all the resistances is RA plus RBC plus RD. We know that since it's a parallel one, 1 by RBC equal to 1 by RB plus 1 by RC. Okay, so now what happens here is, to get that 1 by RBC, it is equivalent to RB plus RC divided by RB RC. Am I correct with this? Because you are experts than me in, especially in mathematics. Okay, so RBC will be equal to RBRC divided by RB plus RC. Am I correct?
Excuse me, sir.
Yeah.
Sir, won't RA and RD be of convective heat transfer, sir?
No, it won't be convective. See, suppose if it is a complete composite wall like this, if the wall is composite wall like this, then everything will be conductive resistance only. Suppose if we have, see, for this wall only I have written, is it visible?
Yes, sir, it's visible, sir.
For this wall only I have written.
Okay.
Okay, for this wall only I have written.
T1 is the outside temperature, sir.
T1 is the, T1 is the inner temperature and T2 is the outer temperature.
Okay.
Del T, finally del T is the one. See, suppose if the del T comes in minus, as in the case, our assumption, we assume heat is transferred from left to right. but automatically what happens is if del T comes in minus, the heat transfer is from right to left. That's what, okay.
Okay.
See, in practical cases, especially in our houses, the heat will be transferred from outside to inner one. Okay. Suppose if we consider the inner layer, okay, if you assume heat is transferred from inner side to outer side, then we will be getting the answer in minus. Okay, the minus side indicates that the direction of heat transfer is reverse. Am I correct or not?
Yes, sir.
Yeah, any questions you have? Any questions?
No, sir, it's clear.
Yeah, not only you, I'm talking to everyone. See, if you have a simple
Sure.
composite wall like this, then you will be having all the things as conductive resistances, and it's arranged in series. Okay, so you will be having 1 by H1A and 1 by H2B, which is yeah, 1 by H2A, which is nothing but the hot fluid and cold fluid convective resistances, and conductive resistance is nothing but L by Ka into A. So the conductive resistance, in case of conductive resistance, the important property which helps in heat transfer is thermal conductivity. Okay, so it depends upon the thermal conductivity of the material. Whereas in case of convective heat transfer, the convective heat transfer coefficient, which is the important property. So in case of convective heat transfer coefficient, the H value will be in watt per meter square Kelvin, whereas here the K value will be in watt per meter Kelvin. Okay, so that particular thing you have to understand. Okay, is it fine, students? Is it fine?
Yes, sir.
Yes, sir.
Okay. So I have given the problem, right? I have already given the problem there in the chat box. Am I correct? Both the
Yes, sir.
problems. Whether all of you are able to see that those two problems.
I see.
Shall I solve the first one? This is the
Okay, sir.
first problem. Okay, let me solve it. Okay, all of you please have calculators with you, because this type of problems will be asked. Please understand, composite wall problems, composite cylinder problems, and composite sphere problems will be asked. Okay, so after next week I will give you the first assignment, which involves all the three problems: composite wall, cylinder, and sphere, so that it will give some idea for you people to solve the problem. Okay, so a furnace wall is made up of 3 layers of thicknesses, different thicknesses: 250 mm, 100 mm, 150 mm respectively. The thermal conductivities were 1.65 for the inner one and 9.2 for the outer one. The inside is exposed to gases at 1250 degrees C with conductivity transfer coefficient 25, and the outer and the inner surface is at temperature 1100 degrees C, and the outside surface is exposed to air at 25 degrees C, and the air convection coefficient is only 12. Okay, determine thermal conductivity of the middle layer, heat transfer per unit area, and interface temperatures. Okay, so now one thermal conductivity is missing. Am I correct? Shall
Yes,
I
sir.
solve this? One thermal
Yes.
conductivity is missing. Okay, actually it consists of 3 layers. Is it visible to you all?
Yes, sir.
Yes, sir.
Okay, so the first layer is 250 mm, the second layer is 100 mm, and third layer is 150 mm. So this is 250, this is 100, and this is 150. Okay, so you have to convert that mm into meter, students.
Yes, sir.
Okay, and let this be K1, this be to K2, and this be K3. So it is mentioned K1 is given 1.65. Am I correct?
Yes, sir.
And K3 is mentioned as 9.2.
9.2.
All of you are able to see this, what I am writing?
Yes, sir.
K2 is, we don't know K2. So that's what we are asked to find out. We are asked to find out what is Q, what is K2, and similarly interface temperatures. Okay, now we have two things. Okay, so assume that the inside gas temperature is 1250. So T suffix A as inside gas 1250 degrees C, and HA convective heat transfer coefficient, how much it is? 25. H suffix A, which is equal to 25 watt per meter squared Kelvin. Okay, so this is hot gas on the inner side. Is it fine, students?
Yes, sir.
Hot gas. Okay, surrounding outer atmospheric air is colder side. T suffix B, which is equal to how much? 25 degrees C. Okay, and H suffix B, which is equal to 12 watt per meter squared Kelvin. Am I correct? Is it visible?
Yes, sir.
Please
Yes, sir.
say here faster.
Yes, sir.
Yes.
Visible, sir.
Okay. Now we know that, and so assume this inside temperature as T1, this as T2, and this as T3, and finally we have T4. Or let me draw it again. We have a composite wall like this. T1, TA hot gas temperature, from hot gas to the inner wall. T2, T3, T4, and then TB. Okay, so the heat transfer is like this. Is it fine, students? Is it fine?
Yes, sir.
Yes, sir.
So we
Yes,
are
sir.
asked to find out what is T3 and T4. So TA is given. TB is 25 degrees C. TA is 1250, and inside surface temperature is 1100 degrees C. So T1 is also given 1100. Am I correct or not?
Yes, sir.
All of you are able to understand?
Yes, sir.
So the heat transferred Q is, we know that first by considering the first convective coefficient alone, Q equal to TA minus T1 divided by uh, the resistance, convective resistance, or RA. So TA minus T1 divided by 1 by HA into A. What about the area? Surface area, whether they have given? They have not given anything about the surface area. Am I correct?
Yes, sir.
Sir.
They have asked us to assume unit areas.
Yeah, assume area as 1 meter squared. Okay, for per meter squared area, you have to find out. Okay, so TA minus T1, 1250 minus 1100 divided by 1 by how much it is? 25. So how much Q? It is 150 into 25. How much, ma?
3750.
3750?
3750, sir.
Sir.
3750.
3750 watts. Am I correct?
Sir.
Okay. Now we got this 3750. Now we are expected to find out the the thermal conductivity of the middle layer. Okay. We know K1. K1 is 1.65 and K3 is 9.2. Now just like this, we have to assume. Okay. We have to assume like this. We have to refer this diagram, and the circuit should be, the total resistance should be like this. Okay, the total resistances should be like this. So now what we have to do is, we have to draw the circuit, thermal circuit, TA, T1, this is 1 by HA into A, T2, L1 by K1 into A1, L2 divided by K2 into A2, kindly bear with me because I am writing it on a smooth surface, ma. Please understand that. And the last one is again convective resistance. Am I correct?
Yes, sir.
Yes, sir.
Okay. Now this is we know that Q equal to TA minus TB divided by sum of all the resistances. Okay. Now we know that Q equal to 3750 and TA and TB we know that 1250 and 25. Okay. So 3750 which is equal to 1250 minus 25. Am I correct, ma? Am I correct?
Yes, sir.
Students, am I correct, ma?
So 3.061, sir.
Okay, I don't want the answer here. I'm just writing the steps. Okay. So yeah, you are brilliant. Hats off to you. Let me write the steps. Okay, for others. 1 by HA into A, 1 by 25. Okay, please tell me. The first resistance is 1 by HA into A. 1 by 25, Amma? Okay. 1 by 25 into 1. And what about the first one? Here we know that L1 by K1 A1. What is the length, ma? Thickness? 250 mm. Am I
250,
correct?
sir.
So you have to convert it into meters. 250 mm. So 0.25. And what is the K value? K value is 1.65. So 0.25. Some of the students they mistake here. They will do the mistake here by putting 250. 0.25. What is the K1 ma? 1.65. Am I correct?
Yes, sir. Yes, sir.
What about
Yes,
the
sir.
second thickness? It is 100 mm. Okay, and we don't know what is K2. So 0.1 divided by K2 into 1, assuming unit area. And the last one is 150. 0.15 divided by what is K3? Final thermal conductivity?
9.2.
9.2. All of you are able to understand ma how I am doing this?
Yes, sir.
Yes, sir.
And finally, the last one, 1 by HB into A. What is the outer convective heat transfer coefficient? 12.
12, sir.
12. HB is equal to 12. Yeah. 12 into 1. So how much it comes? One of your friends said the answer, K2 value. How much it comes, ma? How much?
Sir, 3.0612, sir.
3.0612. So, which implies K2 equal to 3.06, amma? How much?
Yes, 3.0612 meter watt meter cube, sir, degree Celsius.
Watt per meter Kelvin it will be, or watt per meter degree C.
Degree C.
Watt per meter Kelvin ma or watt per meter degree C?
Sir, degree C.
3.06.
Degree C, sir.
Yeah. Okay, both are equal only. Watt per meter Kelvin and watt per, see in the first class itself I have told you. Watt per meter Kelvin and watt per meter degree C is equal. When it comes
Yes,
in the
sir,
denominator,
yes, we can write either way, sir.
yeah, yeah. And now after getting it, we know T1. Now you are expected to find out T2, T3, T4 by using the other values. Okay, individual resistances. Okay, now we got this K2 value. Now find out what is T2, T3 and T4. So how to get T2, T3 and T4 just like the previous class. Okay, we have to substitute. We have to take the individual resistances. Q which is equal. Am I, is it visible ma?
Yes, sir.
Q equal to 3750 which is equal to L1, sorry. T1 minus T2 by L1 into, sorry, L1 divided by K1 into A1. Okay, so now we in the question we know that what is T1. In the question we know that what is T1. T1 is mentioned as 1100 degrees C, right? So considering the first resistance circuit, okay, so T1 to T2 is L1 by K1 A1. Am I correct, students?
Yes, sir.
We know T1. Okay, to get T2, Q equal to T1 minus T2 divided by L1 by K1 A1. Okay, so that's what I have mentioned here. Q equal to T1 minus T2 divided by L1 into K1 A1. So now substituting it, 3750, which is equal to T1 is 1100 degrees C minus T2 divided by L1. What is L1? L1 is what is the thickness of the first layer? 250 mm. Okay, and thermal conductivity is 1.65. Am I correct?
Yes, sir.
Am I? Okay. So now what happens here is 0.25 divided by 1.65 into 1. Now from this, which implies T2. T2 equal to how much?
531.8.
531.81
0.81.
degrees C. Okay, so due to the lesser thermal conductivity of this, the inner layer, so the T2 temperature itself drops. Okay, now similarly take the second one. Okay, take the second resistance. Now we have got T2. T2 minus Q equal to T2 minus T3 divided by L2 by K2 A2. So now you have to write like this. Q equal to equal to T2 minus T3 divided by L2 divided by K2 A2. So T2 we have got 531.8 minus T3. And what about the thickness, ma? Thickness of the second layer? How much it is?
100 mm.
100, sir.
100 mm. Okay, so 0.1, and we have found out K2 as 3.06. Okay. 0.1 divided by 3.06. Am I correct, ma?
Yes, sir.
Sir, I'm getting K2 as 2.81, sir.
Yes, sir. I'm
Awesome.
also getting 2.
Yeah, sir. Mistake, sir. It's 2.8, sir.
2.8, ah?
Sir, yeah, sir.
2.817.
Okay, fine.
2.87.
Very good. 2.81, ah? How much, ma?
Yes, sir. 2.81.
Yes, sir, 2.81.
81, ah? Okay, no issues. Let us change here, 2.81. But anyway, it's that T2 value won't get affected. Okay, only T3 value will get affected when you put 3.06. Am I correct? Am I correct
sir.
or not?
Yes, sir.
Ah.
Yes.
Now substitute 2.81 and get me what is T3.
Sir, I'm getting 398.35, sir.
398.35.
35.
Yes, sir. I'm getting 398 too.
Okay, 398 degrees C. And finally, take the last circuit. Okay, so you can take T3 minus T4, or sometimes you can take T4 minus TB also. Nothing wrong in it. Okay, to get T4, either you can use this resistance T3 minus T4 divided by L3 K3 A3, or you can use T4 minus TB divided by 1 by HB into A. So in both the cases, it will be correct only. Okay, you try that. Let me take T3 minus T4. You can try T4 minus TB. So last resistance Q equal to T3 minus T4 divided by L3 divided by K3 A3. So Q is 3750, which is equal to 398.3 minus T4 divided by L3. What is the thickness again? Final ma 150 mm.
Yes, sir.
150 mm and thermal conductivity is 9.2. Okay, since higher thermal conductivity, more heat will be transferred.
So is it 337?
I'm getting the same, sir.
0.15.
3.
What is the thermal conductivity? 9.2.
9.2.
9.2. How much you are getting? T4?
So T4 337.
337.2
Yes, sir,
degrees.
337.2.
330?
7.
337.5.
Okay, ma, very good. So there is no deviation since due to higher thermal conductivity from 398 it reduces to 337 only because the thermal conductivity of the last layer is very high. Okay, so this you can get T4 by this also. Q equal to T4 minus TB divided by 1 by HB into A. Even when you substitute this also, you will be getting the same answer. 3750, sorry, 3750, which is equal to T4 minus 25 degrees. Yeah. What is the outer temperature given?
25.
25 degrees and HB is 12. T4 minus 25 divided by 1 by 12. When you substitute this also, you will be getting the same answer. One of you please check it and tell me whether the T4 is the same 337.
Yes, sir. It is the same. 337.5, sir.
Yeah, okay, very good. So like this, you have to solve the problem. My request to you people is try to solve the other problem also. Okay, this problem. Okay, now here, students, the same procedure you have to follow. The same procedure you have to follow. Only thing is, here you can see here 2.5 centimeter, 7.5 centimeter, 5 centimeter, and the area is 0.1 meter squared. It is mentioned. Okay, so the thickness is given and the area is given as 0.1 meter squared. So for area, cross sectional area for flow for B, you consider it as 0.5, and for D you consider it as 0.5. Is it okay, students? Students?
Yes, sir.
Yes, sir.
AB equal to AD, since both are equal, the A suffix C cross sectional area is 0.1. So since AB equal to AD, 0.1 divided by 2, you can consider it as 0.05. I told you 0.5. I am sorry, 0.05. Okay, students? Is it okay?
Yes, sir. Okay.
So consider the area of B and area of D as 0.05 meter squared. Is it fine, students? Is it
Yes, sir.
fine? Shall
Yes,
you
sir.
do this problem tomorrow?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
Okay, ma. Okay. Yeah. Let me